Okay, working number 19. We're doing the double integral over the region R of x, y, dA, where we have the region bounded by the line y equals x, which is here, y equals 3x, which is here, and then the hyperbolas we have x times y is 1. If we solve for y, we get 1 over x. This is the graph of 1 over x in the first quadrant. And then x times y equals 3. If we divide by x, we get y equals 3 over x, which is basically 1 over x just multiplied by 3. So it just stretches it out vertically. So this one will be above this one. So the region you can see bounded by the four curves is here. And that's a rather complicated looking region. So let's see if we can convert it into something nicer. Here's the transformation which they give us again. And so I'm going to try and do this transformation. I'm going to take each one of these and see what they turn into. So let's start with y equals 3x. Let's see where that goes. Y equals 3x. So y is actually v, and 3x would be 3 times u over v, like that. And then I multiply both sides. We get v squared equals 3u. Or you could say, how do we want to do this? We can have that u is a function of v or v is a function of u. I'm going to try and make v a function of u, so I'm going to do v equals plus or minus square root of 3u. I'll deal with that in a second, okay? Let's see what happens to y equals x. Y equals x turns into v equals u over v, and we're going to have the same story here. V squared equals u, so v equals plus or minus root u. Okay, let's see what happens to xy equals 1. So x is u over v times y, which is v, that's a v, equals 1. The v's cancel, we get u is 1. That's very nice. And then finally, oh, I got my colors wrong. Oops, this was the blue one. Oops, I'll just redo it real quick. Y equals x, so u over v equals v. No, other way around. V equals u over v, same thing, but v squared equals u, v equals root u plus or minus. Okay, and then that one was nice, and then which one am I missing? The green one, which is xy times y equals 3. So x, which is u over v, times y, which is v, equals 3. So you get u is 3. All right, let's see if we can draw this in the UV plane. Let me erase this. Just remember, that's the region R that I just erased. I'm going to try and see what the image of that is under this transformation. So we have, let's do the easy ones. U is 1. This is u and this is v. U is 3. So that means these are vertical lines. This. Well, you know what? I may as well use the colors. I have them, and I've got some time right now. So, okay. So the green one turns into this. The black curve turned into this. The blue curve. Okay, so we have plus root u minus root u. So we're going to have root u looks like this, right? And negative root u would be the bottom one, but I'll talk about that in a second. And then the red one would be plus or minus root 3u, which is the same as root 3 times root u. Root 3 is bigger than 1, so basically this is going to stretch this one out just to make it a little taller. So it looks like this. Let's just say. All right, so this is v equals root u. And this one's v equals that one was root u. This one up here was root 3u, sorry. Root 3u. And then I've got my two bounds on my u. So the question, I guess, becomes, which, do we take the positive or the negative, right? Because I took both the positives for this. Well, you can see that the reflection of this, right, if you reflect it down, which would basically give you the same region, just over down in the fourth quadrant, why wouldn't something like that work? Let's check this out. Let's just take an example of a point. So if we did the negatives, I'd be down here. If I pick a point over here, let's see, I would have a positive u value and a negative v. So I'd have a positive u and a negative v, right? Positive u value, negative v value. And that would be a negative number, and that would mean x is a negative number. So if you go back to the original drawing we had, remember we were in the first quadrant, and so it would be impossible to get a negative x number. So I can't use the bottom region because that would not correspond to the original region when I go backwards. So we eliminate this. I hope that made sense. So here's my region S. It's that region in there. Now I also need the Jacobian determinant, so I can erase this stuff. I don't need that anymore. By the way, that's a nice type 1 region for a double integral. I've got, if I draw vertical little line segment here like this, as I move that left and right, the red one's always on top, the blue one's always on the bottom. My u's are bounded between 1 and 3. It's pretty simple. But to get the Jacobian determinant, I need the partial x with respect to u, partial y with respect to v, minus partial x with respect to v times partial y with respect to u. So what is the partial of x with respect to u? Remember, x is 1 over v times u, so I'm treating 1 over v like a constant. This will be 1 over v. Partial of y with respect to v is 1, minus partial of x with respect to v. Well, now u is a constant. This is the same as v to the negative 1 times u. So the derivative of that is negative 1 over v squared times u. And then partial of y with respect to u is 0. So that's good, that kills that off. So we just get 1 over v. All right, a couple of more things to do here. I need to come back over to this double integral. I'm going to do the double integral over the region S. X times y, which is this times this, which is just u, times the Jacobian determinant, which is 1 over v, and then with respect to area. Okay. Now, let's go ahead and set up the limits of integration. So this becomes integral, let's see, u is going to be the one stuck between two constants, so 1 to 3, and then root u to root 3u, and I'm integrating u over v dv du. Good. Now let's go ahead and do this integration. We cannot split this up into two using that special thing because these are not stuck, both stuck between constants, so we can't do that. So I've got to integrate with respect to v first. So I've got integral 1 to 3. Now the antiderivative of u over v, remember u over v is u times 1 over v. So u is a constant here. Antiderivative of 1 over v is natural log v. So I'm going to get u times natural log v evaluated from v equals root u to v equals root 3u, and then all of that du. Now that's equal to integral from 1 to 3 of, let's start plugging things in here. All right, if I do root 3u in here, I'm going to get u natural log of root 3u, and then minus, when I plug in root u, I get u natural log of root u, whatever that is, du. And check this out, I'm going to use properties of logs here. Remember, this is natural log of u to the half. The other one over here is natural log of 3u to the half. And so these powers can come out. So I'll do it right here. So I'm not doing any integration yet. This is u, oh, the 1/2 came out. 1/2 u natural log 3u, and then minus 1/2 u natural log u du. And a couple other things I can do here. This right here is a product inside of a log, so I can split it into 2 logs. I'm, again, using more properties of logs here. So I'm going to do equals, how about they both have a 1/2? So I'm going to pull 1/2 out, integral 1 to 3. So I have u, and then remember this splits into 2 different things, natural log 3 plus natural log u. And then minus the half already came out, u natural log u. That, I guess I can put parentheses out here like that. Du. Okay. And then I'll distribute that u through 1/2 integral 1 to 3. So I'm just going to distribute the u through here. I get u natural log 3 plus u natural log u, and then minus u natural log u. Ooh, that's nice. Du, and these cancel. Something tells me I should have seen that earlier. It's okay. Keep it going. Natural log of 3 is a constant. I'm going to bring it out. Natural log 3 over 2, integral 1 to 3 of u du. That's the only thing left, which is natural log 3 over 2 times 1/2 u to the 2nd power, evaluated 1 to 3. And I think I'm getting close here. Plug in 3, we get 9. And then, so we'll get something like 9 natural log 3 on top, and then 2 and this 1/2 over 4 minus, when I plug in 1, I get 1/2. I get natural log 3 over 4, which is 8 natural log 3s over 4, which is just 2 natural log 3, which you could rewrite as natural log 9 because the 2 could go up as a power. So natural log of 9, or the book left it as 2 natural log 3. Okay, that's it for 19. Interesting problem.